So I will talk about the ranking of the drivers of the Martian bow shock based on two mission datasets, MAVEN and Mars Express. And I apologize for eventually those who already had this talk before, probably in the MAVEN team. There is that in physics, we often face with problems where we try to identify relationships between several parameters to identify cause and consequences in a problem. And we often look at scattered data with the correlation factors and so on when we do statistical analysis. And we may face in such cases with spurious correlations like this one example, which is, I hope, a spurious correlation between the US spending on science and suicides. And actually, we often have little difficulties with spurious correlations in physics, since we often know that we have parameters that are related to another one due to physics. But we often face with a problem where we may underestimate or overestimate a correlation between two different parameters due to existing cross correlations with other parameters in a complex system. And this is exactly what we have in systems in planetary environments, such as the Martian environment, where we have the Martian bow shock due to the interaction between the supersonic solar wind and the Martian environment. And this bow shock is eventually influenced by a number of different parameters that you have here in the sketch. And some of them may be cross-correlated, of course. So we have, among the most important drivers, we have essentially here the magnetosonic Mach number. That is a strong driver of the shock, since the shock is a standing fast mode magnetosonic wave at Mars, and its shape depends on the magnetosonic Mach. We have the solar wind dynamic pressure, which will push more or less the shock location. We have also the IMF, the Interplanetary Magnetic Field characteristics, the various angles between the normal vector, the magnetic field vector, and the velocity vector. And we have the intensity of the field itself, and we have also other angles such as the clock angle, or what is called the spacecraft angle from the IMF, which corresponds to the projection in the terminator plane of the angle between the IMF and the location of the spacecraft during the crossing of the boundary, the shock boundary. This was used actually a lot in the Venusian literature for Pioneer, for example. So we also have two other drivers that are important, which are the extreme ultraviolet fluxes of the sun, which will induce further ionization of the atmosphere, and thus more pressure, but also more mass loading, and thus will impact strongly the shock, as was shown before with Mars Express already. And last but not the least, we have the crustal fields that are remnant magnetic fields kept in some of the rocks, mostly in the southern hemisphere of Mars, that are traces of the old global dynamo magnetic field of the planet. And these will act as an enhancement of the pressure, internal pressure, and also interact with the ionosphere itself to push the shock further. And for a number of them, the clear influence, the quantitative influence of these drivers was difficult to establish, in particular for the AMF or the crustal fields, and for some of them it's better known, since already Mars Global Surveyor for some of them. So I used in my work a specific method based on the extrapolated terminator distance, which is a one-dimensional approach, where for crossing, for example, the shock here at point M, we extrapolate until the terminator plane just to get one variable, which is RTD here, based on a conic shape that fix the focus and the eccentricity, but then you recalculate the simulatus rectum to get a variable RTD depending on the location of the spacecraft, and you get an inflation more or less of your shock, which is a classic approach for boundary crossing analysis. So I did two different studies. The first one corresponding to two different papers last year. The first one corresponding to the specific influence of crustal fields on the shock location, and then the second one on comparison between the various drivers. And for that, I used specific methods in addition to classic ones, which are partial correlation approach and also lasso and an AIC, which I will describe a bit later. So just to underline the need to look at cross correlations and to avoid biases in the interpretation, you can see here a sketch, the same sketch as before, just for MAVEN, where I showed the lines with a thickness that is directly given by the correlation factor between the different drivers themselves. So the larger, the stronger the correlation, the direct correlation. So you can see that there are a number of parameters that are actually cross-correlated to each other between Mach, EUV, solar wind area pressure, etc. More or less. For some of them, it's all, of course, expected, such as the Mach number that depends on the IMF intensity. But some others, it's not expected, such as the crustal fields versus the EUV fluxes, which was the case in my MAVEN dataset, which was actually due to simply the bias due to the trajectory of the spacecraft during the various periods where I had crossing datasets. I used for that the Fang and Grisbeth datasets, for those who know, for MAVEN. And we had indeed periods where we had more or less crustal fields located below the spacecraft, while we had specific regimes of UV. So we had some biases for MAVEN. And actually, for example, to take into account biases due to such cross-correlations between crustal fields and EUV that will bias the interpretation of who has the most influence, EUV, crustal fields, and which is the importance of each one. I first used what is called the partial correlation approach. So to understand that, you have here a sketch of 3 variables corresponding to 3 types of information. And if we want to get a correlation factor between the variables 1 and 2, but removing the cross influence of the variable 3, in this case, you will try to get this white area corresponding to the cross correlation, the correlation factor between 1 and 2, without 3. So to do that, you calculate first a regression between 1 and 3, getting the shared information between both variables. You calculate the residual corresponding to the green plus white area. And you do the same for the regression between 2 and 3. You get the residual corresponding to the blue plus white. And then you calculate the correlation between the 2 residuals, which gives you exactly the white area corresponding to the correlation factor, removing the cross influence of variable 3. Of course, this is very simple when you have one variable of influence, but if you have n variables of influence, then you have to do this recursively, and you can do that rather easily with R language, for example. Let's try an application with the crustal fields influence, just simply, but it's something I did for all of the parameters. You can see here first a direct analysis, classic, with the RTD distance of the shock, so in 1 dimension, as a function of the angular distance from the main source of the main crustal source, which is located in the southern hemisphere. So you would expect that the closer from the main source, the strongest source in the southern hemisphere, the further the shock, which is the case. Here you have stronger, larger RTD values than further from the main source. And it's also the case for MAVEN and MEX for Mars Express. You have a quite similar profile for both. But still, you have a difference between both missions with a larger apparent influence of the crustal fields. In the case of MAVEN, you see a larger amplitude here compared to Mars Express. And actually, this is due to the cross-influence of EUV. If you remove this by calculating the residuals, removing the influence of EUV, you calculate the residuals here, and you show that for MAVEN and MEX, and you get an almost identical profile for both missions. And you can see in this case that using the partial correlation, removing biases due to cross correlations, that sometimes may be significant, you can get much more coherent profiles, much more coherent interpretation than just based on one mission where you don't take into account the cross correlations. So second method I used was the lasso feature selection approach that I will not detail a lot, since I guess in the audience you know that it's a classic method in artificial intelligence. So just a regression here with coefficients, and also mostly a variable penalty term to avoid overfitting, penalty term over the sum of the coefficients. And this gives you the coefficients for each of the drivers that are shown here for MAVEN and for Mars Express on the right. And you can see that the larger coefficients correspond to the magnetosonic Mach number, to EUV, to also the angle theta BN, meaning that quasi-perpendicular shocks lead to further shocks compared to quasi-parallel. And then solar wind dynamic pressure, the crustal fields through the angular distance, and other drivers for the IMF in particular. And some of them, some of the coefficients get shrunk to null very rapidly for some of them. For example, Vn here. And it's quite similar for Mars Express, though we have no magnetic field data for Mars Express, so it's not possible to compare for some of the parameters like magnetosonic Mach or the IMF parameters. And then I used what is called the Akaike information criterion method. It's an information theory-based approach that is used, that is dedicated to rank models, actually. And how does it do, actually? It estimates the amount of information that is lost by a model compared to another one, or compared to a dataset. And this provides a score that is given here, and that depends also on the number of variables to avoid, again, overfitting in this case. And you can use also quite similar approach that is called BIC, Bayesian information criterion, that provides quite similar results, but with a more constraining, with more constraints for the to avoid overfitting. So you get in the end scores that you can see here, where actually I removed one by one each of the drivers I mentioned, and you get the larger scores for the most influent parameters according to the model. And I did that for a linear approach or a log approach, which at first order correspond to most of the functional forms. So in this case, you can see that again, we have UV, magnetosonic Mach, and theta BN that are the largest drivers, as for LISO. For UV, for MEX, since we have not these parameters. And then at a similar level, but below, we have the crustal fields, the solar wind dynamic pressure, and then other parameters that keep significant, but others were removed by AIC, such as the VN angle or others. So overall, we get current results for both missions and also for all these three parameters, which show that we have very significant drivers, which are EUV, that are magnetosonic Mach, but also the theta BN angle, which was not expected, not known, at Mars, but was known at Venus or Earth. And I will not enter into details, but it seems that it's not that obvious that the classic explanation given at Earth or Venus is appropriate at Mars, since the anisotropy of the magnetosonic wave velocity this velocity depends on the theta BN angle, does not appear as very influent in this case. And then we have other parameters significant, crustal field, solar wind dynamic pressure, but also possibly other IMF orientation angles that are significant or not, it depends, and it's more complex to give conclusive interpretations, I think, on the IMF parameters. So overall, I think, before I finish with the last slide on other topics, I think it's important to think that when you are looking at statistical analysis based on specific data sets, we have to take care of the possible biases of specific missions, specific data sets, and this comparison between several missions and comparing with several approaches, I think is important to avoid misinterpretations. And in particular, when we're looking at minor drivers, It's very difficult to look at minor drivers with classic methods where you use sub-datasets. You separate, for example, split your dataset into two with a low and high regime for second variable, etc. In this case, if you have many variables of interest, of influence, it becomes very, very difficult to look at minor drivers, since you remove the number of parameters, the number of dataset events, and you eventually get an in-immersion sampling of each of the parameters and so on. So I think this kind of tools are quite powerful for that. And if I have, I don't know how much time I have left, but if I have a few minutes left, I can talk quite rapidly about a few topics I've been working on for machine learning or deep learning. I could actually discuss a bit further in other talks, since I think you are an audience mostly interested in such topics. So I worked on different topics, some of them being published and some others not. First, I worked a lot on with a PhD student on the detection of the core region of reconnection events at the Earth magnetopause with the MMS mission. So we did that with the publication in 2021. The idea was to detect the core of the reconnection region that is very small and very difficult to determine. And we had only a bit more than 20 events after a few years of mission, and we tried to increase this number by an automatic detection. For that, we tried an MLP approach with a very variety of features, and then we also used a CNN approach, since the first one had lots of false positives, since we are in a situation where we have a very rare event case with very highly imbalanced data set. So we tried CNN then, which worked pretty well to detect such kind of asymmetric distribution functions for the electrons, where we have a strong anisotropy with a crescent that you see here on the right, which is a sort of signature of asymmetric reconnection. So that's the first topic. Then I worked a lot also on Rosetta. And in particular, I worked with a colleague on the automatic detection and classification of dust images by one of the microscopes on Rosetta, which was COSIMA. And the objective was to provide constraints on the dust properties, in particular to understand whether they were fractal or compact and so on, to understand the comet formation conditions. And the automatic detection worked pretty well, but classification not that well, since we were unable to classify ourselves. So in the end, so the algorithm that was as bad as we were, not better. And last, maybe of interest for some of you, we've been working a lot on at IRAP on the labeling of plasma environment data with various techniques, in particular on the detection of Martian bow shock from MAVEN Mars Express, and also Venus Express for Venus. So this is currently in progress. And we want to do science with that, but also to implement the algorithms inside the planetary database that is called CDPP-AMDA to provide some added value for the community, so that they can have a very easy interpretation at first of the data just by some automatic labeling of them. And I think I will stop there. Thank you very much.